I want to try to illustrate that there's more to the Pythagorean theorem than just determining whether or not triangles are right triangles. So here I have a side with label lowercase a opposite the angle given with capital A. The side with vertex B across from, or the vertex given by capital B across from the side with lowercase b, and C customarily is the name for the right triangle, the right angle in a right triangle, and it's across from the hypotenuse, as you know. So I'm going to construct squares on the sides of this triangle, and we're going to do a little more exploration with the Pythagorean theorem. So I've just created a line through BC and then created a line parallel to it here at vertex A, and I'm going to create a segment on AC that I can rotate 90 degrees clockwise. Transformation tool, rotate segment B around C 90 degrees clockwise, and I'm going to rotate now this segment around A another 90 degrees clockwise, this segment around C another 90 degrees clockwise. And I'm going to turn off the line. And let's see how this thing moves. So the area created on AC is going to change based on the length of AC. And that's kind of what I want to have happen. So let's go ahead and create a segment here on BC, and let's rotate that segment G 90 degrees. I'm going to go counterclockwise on this one and rotate this counterclockwise. Okay. And rotate again counterclockwise around D. Let's see how that moves around. It's kind of cool. And let's make one more segment. And I'm going to go ahead and create those polygons. If I really wanted them to be different colors, we could go to the properties box and change the color. But for now, we have a triangle with squares created on each of the sides. We won't call them legs until they are in a position where there is a right angle. So let's get an angle measure in here. And I'm going to go to the rounding tool and go to 0 decimal places. Here's my right angle. I kind of like that to pop into right at some point. And I'm just not going to be able to get it precise enough. Okay, so here's what we have to work with. The idea of the Pythagorean theorem is that you can use it to test whether two triangles are right triangles. One of the ideas, that is. So if you square two sides, two legs, and they equal their area equals the area of the third side, then you know you have a right triangle. But take a look at what happens to the area on C, this area here. Take a look at what happens to this area when the triangle gets more and more and more acute. Well, the area of these two squares is clearly larger than the square created on C. We go back to what is accepted as a 90-degree angle, or close to it. And we can determine that breaking this square up and this square up into pieces that fit into this square, we will find an equivalent area. When I add these two areas together, they'll fit into this area. One will map directly onto the other by a series of rigid transformations. But what happens when the triangle is obtuse? The area on C squared, as the triangle gets more and more obtuse, is clearly larger than the area on the two sides. So tonight's homework helps you to identify this relationship algebraically. When C squared is smaller than the area of A squared added to the area of B squared, then the triangle is acute. And when the area of C squared, what happened to my triangle moving? When the area of C squared is larger than the area of A squared added to the area of B squared, then your triangle is obtuse. The directions are given on the handout 3-10, what type of triangle, and there's 8 exercises for you to work with. You're going to work with the triangle inequality theorem. Maybe you have to look that up. This is going to be for performance in your operational proficiency category. So attend to accuracy and precision.